Hi, my name is Sadman Binzaman. This is EL6303, assignment 12, question number 2. We're given x of t, which represents a deterministic signal, f of t corrupted by noise. X of t is passed through a receiver with impulse response h of t. We're shown that h of t equals f to minus t is the best receiver that maximizes the output signal to noise ratio, where the input f of t is a deterministic signal and n of t is white noise, WSS white noise with unit spectral density. TO represents the output decision instant. We're asked to plot the filter response h of t when the input f of t is a rectangular pulse of duration t, and the output decisions are made at t initial equals capital T, t initial equals t over 2, and t initial equals 2t. Since we're dealing with a linear process, and we know x of t equals f of t plus that white noise n of t, we can basically interpret this as f of t going through that receiver followed by n of t, and as an output we have y of t equaling y f of t plus y n of t, and we know that y s of t can be defined as that f of t convoluted with the impulse response h of t, and y of n t is similar in that it is the initial n of t convoluted with the impulse response h of t. Next, we know that the signal to noise ratio equals the output signal power at t equals t initial over the average output noise power, which in turn is defined as the absolute value of that yf t when t initial squared divided by the expected value of ynt squared. Remember, we're doing all this with the assumption, with the goal of maximizing our signal to noise ratio at time instant t0. Before we continue, we need to revisit a few things. We know that the frequency response h omega is defined as the integral from negative infinity to infinity of h of t times e of negative j omega t dt. And we know that the power spectrum sy omega equals the Fourier transform of the autocorrelation of tau, which equals the power spectrum xy omega times the frequency response, and that in turn equals the power spectrum x omega times the absolute value of that frequency response h omega squared. So knowing that, we can go back to our problem. So the last thing we went over was that the signal to noise ratio was defined as yf t initial squared divided by the expected value of ynt squared. And keeping in mind the stuff that we just went over with respect to the power spectrum of the frequency response, we know that we can simplify that to equaling 1 over 2 pi times the integral from negative into infinity times the power spectrum omega times the frequency response omega times e to the j omega t initial d omega squared divided by 1 over 2 pi of the integral negative infinity to infinity of the power spectrum omega times a frequency response squared d omega. So one of the things we need to know is that the simplest input noise model assumes that n of t to be white noise with spectrum density NO, and in our case we have that being so we know that our we have a unit spectral density, so that NO equals 1 in our case. So we know that the signal noise ratio equals what we had up there, except we can simplify that to equaling the integral from negative infinity to infinity of s omega h omega ejwto dw squared d omega squared divided by 2 pi, that spectral density, times the integral negative infinity to infinity of h omega squared dw. I'm really sorry, but it looks like my camera is having trouble recording it, but we'll try to work this out. So the textbook suggests the application of the Cauchy-Schwarz inequality. So we know that that signal to noise ratio is going to be less than or equal to 1 over 2 pi, that's times that spectral density, times the integral from negative infinity to infinity of the power spectrum squared d omega, which equals the integral from 0 to infinity of our function up here, f of t squared dt, divided by our spectral density, which equals, that's fine. So the book goes on to say that the signal to noise ratio equals this, meaning we could disregard the less than, when the frequency response equals the power spectrum times e of negative j omega t o, and that h of t, our impulse response up there, equals f t o minus t. Okay. So this applies to, when we're dealing with casual systems. Okay. But we're asked in part B when TO equals T over 2. And that is an example of when the receiver is not casual. So the book goes on to define that the the impulse response, the optimal impulse response, equals f to minus t, similar, but then we're going to tack on a unit step function, u of t. Okay. And to maximize the output SNR, the signal to noise ratio, that's going to equal 1 over the spectral density times the integral from 0 to TO, which in case of B would be T over 2 times f squared, f of f squared t, meaning that function that we had up here, dt. All right, thank you so much. Again, I'm really sorry for the technical difficulty we had with filming this.